Okay, good morning or good noon, everyone. My name is Amit, and we're going to talk about the natural language understanding orchestra. So first, a few words about my employer, Booking.com. So you probably know it's the biggest accommodation website worldwide. Most of you probably already used it. What you probably haven't used is our chatbot. We have a chatbot on Facebook Messenger, and you can just search for @Booking.com in Facebook Messenger, and try to chat with us, try to book a hotel with us using plain natural English. So I welcome all of you to try this, send feedback, tell me how it went. I would really like to know. So a few words about myself. I'm a senior machine learning engineer at Booking, and in the past 7 years, I've been working on mainly chatbots for the travel domain. First as part of a startup, then in the last 2 years as part of Booking. And through this experience and during this time, I had accumulated a lot of bugs and challenges and problems that me and my team have seen. So there were a lot of problems that we've faced and a lot of challenges, and I would like to share them with you. I would like to stress that it's not only about chatbots. So chatbots are one type of a complex natural language understanding or NLU product. There might be others: summarization, question answering, semantic search, and each one of them has a lot of models, machine learning models, working in parallel in order to achieve one goal. And I want to take you through this journey of what problems we encountered and how we are aiming to and we are solving them right now. So we will start with a few simple examples in order to demonstrate the problems that we have. This is a simple query: hotel in Warsaw. A very, very simple sentence that the user might type in our chatbot. We want to understand this and we want to serve them the best that we can. So we're doing the first thing that every machine learning practitioner does with this. We tokenize the data. We try to take this string of characters and split it into distinct words, so other components along the path will be able to use these tokens, and it would be easier for them to understand tokens instead of separate characters. Then we try to understand what we see inside these tokens. So usually it's called named entity cognition. I will only focus on one case of this, the location parser. I want to understand which token is a location, which token is means what location in the world. So the token of Warsaw means this place right now with this longitude and latitude and this number of hotels, etc., etc. Every data that I can bring in from my database, and now I know which location the user is talking about. The next thing I'd like to understand is what is the intent of the user? What do they try to accomplish? Why did they come to the chatbot in the first place? In this case, we are talking about searching for an accommodation. So given the intent and given the location that I know, now I can serve some results to the user. I can help them. I can show them the hotels that they're looking for, and now I brought some value, some useful value from my product. So this is a linear pipeline, and virtually all NLU products start with this linear pipelines. One component passes the data to another component, and then another one, and so forth. And I would like to challenge this assumption. I would like to challenge this idea, and I'll show you why. Let's take a different example, the same one, but in Italian: albergo a Varsavia. If we see this, we want to understand the user still, or at least give them a proper feedback. So usually we will add as another component in here, language identification. So if it's English, we are using our current pipeline, but if it's not English, we might have a different pipeline. It might have different tokenization, different names for locations. Or maybe we just don't support it and we would like to say, sorry, but we're not supporting Italian. So we already have not a pipeline, but a place where we have to make a decision, where we need to take one path or the other path. And in this case, this is linear, but just almost, because we're starting to see the complexity creeping in. Let's look at the third example. And the third example is a little bit more tricky. Cancel Eden Hotel. Personally, I can read this in two ways. One, where Eden is a city. There are quite a few cities with this name, and I'm saying, okay, the user is talking about this city. There is another way, which is based on the fact that I can identify the intent. The intent of this specific user is to cancel a previous booking that they have on our website. And when we do understand that, we want to give them the best experience possible. Maybe they just booked a room at a hotel called Eden Hotel, like this. And so I would like to take the intent that I just identified, which use the location, go back to the location parser and tell it, well, maybe you can search a little bit better. Now that we know that it's about cancellations, maybe you can look at the previous bookings of this user. Maybe you can understand the sentence differently. And now we have a feedback loop in this. And this feedback loop complicates things. So which should I run first? The intent classifier or the location parser? Which affects whom? How much time should I go with this loop again and again until I think that my results are correct? So this makes it a little bit complicated. The last example I would give starts again with a very, very simple example, hotel in Cambridge. We tokenize and identify the location and the intent. Seems easy enough. And then we're saying, okay, we assume this is Cambridge, UK, because it's the most popular one. We don't want to bug the users with more and more questions. We just assume this. And we show some results for this. And then the user just types in Massachusetts. So we start again our pipeline. And we identify Massachusetts as a state, because I don't know if anything else that sounds like this. But then we need to identify what is the intent of the user, what is the real action that this user tried to achieve. They tried to fix our results. They tried to fix the location that we thought we understood and saying, no, I meant Cambridge, Massachusetts, not that Cambridge, this one. And in order to identify this intent, we need to have another point of data. This data is the conversation state. We need to know that the user searched already. We need to know that we showed results in UK, and we need to know that we can interpret the location just differently from what we understood. Also, the location parser needs to take the conversation state into account, because the user, they don't want a hotel anywhere in Massachusetts. They want it specifically in Cambridge, Massachusetts. And we want to help them. If I'll show them the wrong thing, they will go away, and for a good reason. So there is the conversation state that creeps in and affects both the intent classification and the location parser. And we can really see with our own eyes that conversations do not behave like pipelines, where you have a very strict order of things and one leads to another and they are all sequential and happily ever after. We see a different pattern here. And this is the problem that we encountered while trying to enrich and add more capabilities to our product. Eventually, this one doesn't scale. Thinking of this as a pipeline is problematic. Okay, so let's enumerate again the problems that we've seen. Conversations are non-linear. Even people are talking about multiple things. They have multiple threads of thought within the same chat. The pipeline metaphor is inherently broken because things are not working sequentially anymore. They also have multiple dependencies and a lot of complexity of what to take into account at each stage. And the same component is called many times with different inputs. So when should we run it? When should we really use it? And when should we say, okay, we're done? That's the problems that we faced. And I would like to change our point of view and look at this as with different architectural choices. So first, I will back away from the pipeline and would say this is a graph. A graph has nodes, a graph has edges. It can have multiple edges for each node. It can have loops, it can have a lot of stuff. but it's not a pipeline. We are not talking about sequential data anymore. But still, even that I flipped the image, we didn't solve the initial problem. For example, the location parser is used in many ways with many inputs and at different stages. So what should we do about this? How should we handle this? And here there is another insight to be seen. We have the task of identifying locations, but we don't have to have one model that identifies them. We can have more than one. So maybe I can have one location parser which only takes the tokens into account and understands locations given the text, what it can, what it can't understand. It won't do this. And then I have a different model. It does the same thing, basically. It tries to contribute results to the same task. But this model also assumes that it knows the conversation state, it knows the intents, maybe it knows the results of the previous location parser. But now that we have two models, each of them have a clearer dependencies, we can move them around and get to the state where we have a directed acyclic graph. And this DAG, for short, is very powerful because these kind of graphs have topological order. They have natural order. I know what can be run at each stage. I know that if I get to a specific node in the graph, everything that it depends on is already completed or ran or something else. So I can really look at this and reason what am I doing, how my flow looks like, and what exactly I need to run at each stage. So with this, let's try to break down what I'm actually proposing for you as a solution. So first, we need to separate the tasks into different models. If I have different dependencies, I want to have different models for them. I don't have to treat each task as being tied to one specific model or to one specific method. So I can have a location parser that uses tokens, one that uses intents, and one that uses the conversation. And they're all contributing to the same result eventually, which is which locations I identified. The second thing is we start to define some kind of standard contract between different components. Let's take the example of the intent to fix the previous location. It has dependencies, and these dependencies are not just locations in general. We want to say we want the simple location parser. We want the English tokenizer to be run before it, and we want to have the conversation state. Without these three components, we cannot run. Only we might have a condition. For the first message, there is no need to run this. We can skip it, basically. And we have the output. And the output is what we return basically to the graph and accumulate over time. And it has two dimensions, this output. It has the type, which is the label, and it has let's call it the result that we wish to fill, or the slot we wish to fill, which is the intent of the user. And by doing this, separating the type from the result or from the task that we're trying to accomplish, we can now have a standard API between components. Each component outputs one type of results. So I've enumerated a few of them. Tokens, for example, are just the words, maybe with some added data. Is it singular? Is it plural? Is it misspelled? Whatever. Spans are basically spans of different tokens that have some value. So in our case, Eden Hotel is a span of 2 tokens, and the type of it is a location, and the value is is a specific hotel with a hotel ID and all the data I can put from the database. We have labels, which are pairs that apply to the whole text. We've seen intent, which is a Boolean label, which means the user whether the user wants to book a hotel or not. But we also have some labels with a lot of data. For example, sentiment analysis. I can have a label which says how much the user is angry or happy with the results I've shown them. Maybe I'm showing them a hotel and I'm asking, did you like it? So I want to identify, I want to classify this, and I want to have this on a scale. And we have the state. The state contains what we previously understood, but also a lot of metadata around the user that we can achieve. So for example, if a user says, I want a hotel for tonight, it's really important for us to understand which time zones they are in, whether they're in China or in the US. It's 2 different days. And we don't want to book them the hotel for tomorrow, and they will come to the hotel and say, oh, I don't have a reservation for today in the middle of the night. So we have this standardization of the API. Now the components can be freely connected and disconnected one to the other, and it's really easy to change the graph according to what we need. The last part of the proposed solution is basically some kind of orchestrator or a conductor. This component is special in that it gets the configuration of the whole graph, and then it runs the models one by one according to their topological order, according to the conditions they have, and passes just the data from one to another according to what they configure as their dependencies. So this part is, in my view, very similar to just a plain web server that just routes the traffic between each model until we complete the request. So this is the solution that I propose. These are the aspects of it, and I would like to argue that it has many, many advantages. The first merits of it are on the software architecture world. This is basically a microservice architecture. We can call it micromodel, we can call it in many names, but it has the same advantages that we all see when we are developing and deploying microservices. Monolithics are obsolete in many ways, and by this way we have very defined components. One can use TensorFlow, the other one can use PyTorch, the third one can use a different technology or a different version. We don't have to argue which one is better and try to cram them all into one process. Also, it's very easy to unit test. So think about this. I have a component. It should identify locations. I know exactly what tests I want to use. What is the output that I expect? I can verify that by itself, each component works correctly. And this is very powerful and really contributes to my development velocity. And the third one is that it's easy to track errors to the specific components. So maybe I've seen that we didn't reply correctly to the user, but so I'm looking at this and saying, oh, did we identify the intent correctly? It seems not, so let's take a step back. Let's look at the inputs that this intent classifier got. Are they all correct? If so, then I know that this component is the one to blame or the one to fix. But if one of them was incorrect, I can go further backward and backward until I can find the root cause of my problem and see how it propagates through the graph from one error, which might not be big, how it propagates to something that the user did not want to see and we did not want to reply. There are another set of advantages. They are more around the machine learning and product practitioner. So it's really hard to write good models. I've tried a lot, and while tokenizers are pretty simple, location parsers or intent classifiers are notoriously hard to tune and reason about and collect data for. And when I have a good location parser or a good parser of any other kind, I want to share it with everybody. I want to share it within my team with different products. I want to make it useful for as many people as I can. And by separating my models to very specific standard APIs, I can really foster reuse of them. Also, it's very easy to extend and be flexible. I have a chatbot, but Booking also have a search box. When you type booking.com, you get a search box. They don't need the intent classification. They don't need to have a conversation state. They just want to understand locations, for example. So they just call a subgraph of my big graph and use its results without calling the whole thing. It's easy to share the same infrastructure. Also, it's super easy to extend. Think about this. I have a big, hairy transformer intent classifier that identifies hotel booking and hotel cancellations and asking for customer support and whatnot. And now I see people are coming to me and telling me you are awesome or you did a great job. They sometimes say this to the bot. It's very nice of them. And I want to reply them nicely. I want to say, thank you. You're welcomed. I don't know. I want to reply with something intelligent. But I don't have the same amount of data that I have for hotel bookings and hotel cancellations. I have just a few examples that have seen this, but I still want to reply them correctly. So I don't need to now find thousands of examples, train my big transformer model with TensorFlow, tons of GPU time in order to carve some space for this intent. I can just say, oh, I will just roll out a model which is a regular expression. When someone says thank you or you're awesome or you were great, I will just reply to them with something. And I can put this model in the graph, a very simple model which is basically 2 lines of regular expression, and I'm almost done. I will say this is high probability. I can now see how it affects the user, how many times it is called, what happened with these conversations where I replied with that. And if I see that I have more data and I have a need for a more sophisticated model, I can just replace it. Now I have 300 examples. I can replace it with a scikit-learn model. I have 3,000 examples. I can put another transformer. I don't know. I don't have to be tied by my task to a specific tool. There is no one-size-fits-all in language or in many cases in machine learning. We need to think that we should be able to take the right tool for the specific job that we need to accomplish. So this kind of graph really gives us the flexibility to try this. It also gives us the flexibility to experiment freely. If I have a good location, I have another location parser. I'm saying, oh, this is great. I checked it and it has its F1 score is bigger by 5%. It's better on my offline data. We should use it. Why should we? Maybe we'll put this and experiment with this. We'll put this inside the graph, and now we'll do A/B testing. We'll direct 50% of the user through the old location parser, the other 50 through the new location parser. And let's see, do users book more? Our users seems to be happier, less angry? Do they look like they found what they looked for? If so, the offline metric really correlates with my product, but maybe it doesn't affect it at all. So this kind of graph makes it easy to experiment and understand how your offline improvements of machine learning models really manifest in your product. So to summarize, I would like to reiterate what I'm proposing as a solution. We should never look at complex NLU products as just pipelines that transfer data from one component to another. They are graphs. And these graphs are made of many models. Each one can be whatever technology we want. It's a service by itself. They are all contributing to the same task. These tasks are well defined. They have dependencies and conditions, and they have standard outputs so we can mix and match. And eventually what we need to do, we have these very simple, straightforward models and just one complex or subtly complex orchestrator that makes sure that everything runs in its turn and returns the result eventually. So thank you very much. I would be happy to get any feedback and any questions here or later. And if you face similar problems, feel free to contact me.
Thank you. Questions? Okay, few.
All right, my question is, great talk by the way. The question is, you propose acyclic graphs, but is it in production?
Yes, we have this in production.
And the second question is how big it is, this graph, like more or less?
So the examples I've shown here are with 3-4 models, something like this. In production, we have, as part of the graph, like 12 or 15 different models, and we have other models that we are currently transferring into the graph that we haven't been able to do so before.
2 more questions. Somewhere here, right? Yeah.
Yeah, hello, thanks for the talk. So I understood your solution as like a handcrafted direct acyclic graph with models specified for some specific case with dependencies. How would you compare that approach to an end-to-end approach where we would try to like solve the whole, like, because this solution requires a human that would model the stuff in a conceptual way first, that we need an intent, we need a location, and etc. And how would you compare it to like an end-to-end approach where we would try to like optimize some final metric of the whole system without doing this?
Thank you for the question. So one option to optimize this is a very, for example, the task of understanding users in order to help them book an accommodation is a very complex task. And it's not always clear what is the end goal. So eventually they should book more. But if someone says, is this hotel wheelchair accessible? And I'm saying, no, it's not. Am I doing anything wrong? Of course not. But they will not book because they need something that is accessible. So it's very hard to measure this. So I prefer to focus on specific areas where I can that I can measure the success in a way that is objective, like did I understand the location? And for the product, I would try to optimize as software metrics like people's happiness, angriness, how likely they are to convert, and see that the product metrics go up, not the machine learning ones of precision and accuracy. In addition, regarding to end-to-end system, I always found it hard to retrain them and to have different sizes of problems within them. So you have a very big model now. Each one needs to add a new intent or add a new type of thing, or you need to tune something. That's usually after the end-to-end system, you just have wrappers and wrappers of handcrafted regular expressions to make sure that you didn't miss Paris or New York or something like this.
One question, last one, somewhere here.
Great talk, thanks. Just for I'm just curious, how many different states of the conversation you track? You said that there are Boolean flags. Yeah.
We are trying basically to understand what is the current flow of the users. So for example, maybe we are at the part where the user tries to filter the results that they've seen, or maybe another flow might be to really specify why they are going on vacation or on a trip. Is this the business trip?
But my question is about the number of those states.
So basically, each flow has a state machine, and this state machine contains usually like 4 or 5 states, but they move from flow to flow, like according to what they accomplished.
Okay, thanks.
Okay, thank you so much for the talk.
Thank you.
Big applause.